Hi, I'm Ben. I am as was introduced, a staff machine learning engineer at Deliveroo. I've been here for around 4 years and been in logistics for that entire time. So I'm going to talk about one of the things which I personally have worked on, but I do want to call out that I'm going to talk at quite a high level about the way that we do the modeling, and it is not only my work. I've worked with a great team, past and present, who have contributed to this, and so I can't take all of the credit for what I'm going to talk about. Okay, to get started, let's first talk a little bit about Deliveroo. I'm sure many of you have heard of Deliveroo. You may have seen our riders around in the streets, and quite a lot of you presumably will have ordered from us. But you may not know the full extent of the company and who we are and what we do. So the first most obvious thing is we're a food delivery company. We take orders from customers to bring them food. And that puts us in the center of what we like to call our three-sided marketplace. So we have three sets of customers that we have to deal with in many ways. We have the consumers, folks like you ordering food. We have our riders who help us deliver the food. And we have our partners, which can include both restaurants and grocery partners from which the food comes from. And we are in the center trying to pair all of these three together and make sure that everyone has a great experience. So to put some numbers on that, which is great to be able to do now. 3 years ago, when I last presented, I had to be a little bit more coy with these numbers. But now that, since we've gone public earlier in the year, I could pull some numbers from our quarterly results. So we are in 12 markets. We reported last month that we had 7.5 million monthly active users across Q3. And we have something like 143,000 partner sites, which is both restaurants and grocery customers. And globally, we work with something in the region of 150,000 riders. So we've got pretty big numbers in terms of the amount of people that we interact with in our marketplace. In terms of the actual team, we announced earlier this year that we're planning to hire 400 new people into the tech org. And this is going to be across engineering, machine learning, data science, and design, along with everyone else. Obviously, this is a pretty huge growth for the team, and we already have a pretty big team full of super smart people that I feel very lucky to work with. And as we said before, we're hiring. But so we're doing a huge growth in terms of our staff numbers. But it's also worth calling out that Deliveroo is very much still a hypergrowth company. Across the last year, we've sort of sustained through each quarter 64 to 114% year-on-year growth. These are still ludicrous numbers. 4 years of them has got me a bit used to them, but these are very large numbers in terms of our growth numbers, which is still super exciting and a huge challenge for us every year as we have to scale our systems to match the growth that we see. In the machine learning and data science side, we cover quite a lot of the business. So the first area, delivery, is where I work. And we focus on our dispatch algorithm, along with some of the predictive models. So things like the prep time model I'm going to talk about today, and rider pricing and some other areas. We also have teams in consumer working on our restaurant list and working on sort of Plus and our loyalties and the various subscription models. In restaurants, we have work on segmentation and menu optimization. We also have things working on an ad platform and various other things. Then from more of a core data science area, we have various folks working across the business, dealing with different sorts of metric reporting, exec reporting, profitability, etc. And of course, running loads of experiments for us. This is just a taste. We have more than what's here, but just give a bit of a flavor of the different sorts of things that we get up to at Deliveroo. All right, that's sort of just a brief overview of sort of how big Deliveroo is and what sort of things that we do. I think it can be easy to forget because our business model is kind of hyper local, as we call it. You only really see it in your neighborhood, just how far spread we are these days. And so in order to think about how we predict preparation time and what we really mean by preparation time, it's useful to first consider the order journey that you have at Deliveroo. And the order journey can be broken down a little bit like this. We have some hungry customer that we want to make a happy customer. They come to our website or our app to place an order. That order gets placed, gets sent to a restaurant who will then confirm if they want it. They have a tablet in the restaurant through which they can do this. They're going to prepare the food, which you can see is in the center of this diagram, and is what I'm talking about today, sort of central to getting the food to you. Then we will go send a rider to the restaurant who will pick up the food. They will bring it over to you, and then we end up with our happy customer. And this is sort of like the sort of simplified broad flow of the order. But so for the preparation time, the thing that we're most interested in is Deliveroo at some point has to tell a rider to go to a restaurant and has to tell a restaurant to prepare some food. And for that, we want to do that such that we have this nice handover of the food from the restaurant to the rider, such that it can then get to the customer. We have the ability to choose when we communicate to our riders and restaurants and exactly what they tell them in order to facilitate this handover. And that's sort of where the preparation time model comes into our delivery network, at least, is in how we facilitate this handover. Of course, a picture like this with one rider and a restaurant makes it look potentially quite simple. But you have to remember that I talked about our scale before. We're doing this lots and lots of times simultaneously across London. So this is an image which shows all of the logged in riders at some point. I can't remember when it's from, in central London. And so we're doing this for every order that's live at that time and considering all the different riders, and have to think about how long it's going to take them to get there, as well as how long it takes the restaurant to prepare. But ultimately, when thinking about preparation times, one of the big things that we need to think about is what can go wrong? What will happen if we get it wrong? And it can be summarized on this slide. The ways in which us getting preparation time wrong leads either to the food waiting for the rider and just sitting there on the side, or a rider getting to the restaurant and having to wait for the food. Ideally, this will happen at exactly the same time. The rider will arrive as soon as the food's ready, and it will hand over very smoothly. But this is how it goes wrong. And so the question of the preparation time in this context is primarily of when to arrive. When do we want a rider to get to the restaurant? Okay, so how do we then think about defining when a rider should arrive at the restaurant? It's not super obvious exactly what the right time to arrive is. And so we can think about where we can get information to work this out. So the first obvious thing that we could do is we can ask our great partners in the restaurants to tell us when the riders should arrive. But if we think a little bit about what the flow in a restaurant looks like, and restaurants vary a lot, it's very hard to talk in full generalities here. But at least in the kitchen, as you can see the chef preparing this food, they're very busy focusing on making sure they're producing great food and preparing it as fast as they can. It's not obvious for them how they would tell us to send a rider if we asked them just to request the rider. They don't know how long it would take us to get a rider there, and how would they know exactly when to request it? They could also tell us when the food is ready, but the flow for chefs in restaurants doesn't typically have a delivery tablet sat right there. In fact, the more common case with the delivery tablets is that they sit with the front of house folks in the restaurant. Which is a little bit difficult for the front of house folks to know precisely when the food is ready and make sure that we get a good signal of actually when it was ready. And if the rider's there when that happens, then maybe they would forget to press the button. Or in general, it's not obvious how it would build into their flow. Secondarily, we'd have to worry a little bit about what the incentives are here. If we were asking restaurants to ask us for riders, we have issues that in situations where our rider network is overutilized, maybe the riders aren't getting to the restaurant as fast as they want. Well, the most obvious thing for them to do is start requesting early so that they get a rider sooner. And this doesn't align our incentives together. If they're going to try and game our systems and request at the wrong time, it doesn't give us the right targets. It's not impossible to get signals from the restaurants like this, but there are a load of complications that make it a little bit difficult, and you can get some sort of anti-patterns if things don't work out nicely. So what else could we do? Maybe we should think of other ways that we can do that. So the other person who's involved in this process is, of course, the rider. The rider has to go and collect the food, and they can pick it up. But when they get there, they won't always know if the food was ready. Just because it's ready when they got there, was it ready for 5 or 10 minutes? They're not sure. But if they are there, then there's a good chance that they will know when it is ready, because they hopefully will get it at the right time. And thankfully for us, in that picture, there was the rider on their phone. And our app provides an interface for the riders as they move through this flow. When they're at the restaurant, they get a screen which tells them precisely which orders to pick up to make it easy to pick up. Once they've collected them, they transition to a screen that helps them get to the customer. And so naturally built into their flow is this communication to us of when they're getting the food. And the things that we get from them across the flow, broadly speaking, they will tell us if they want to accept an order. They'll tell us when they've got to the restaurant. They tell us when they've got the food, and they tell us when it's delivered. There are other signals that we can get from riders, but these are sort of the relevant ones here. And we can use these to try and work out when the food would be prepared. But we do still have this problem that maybe the food was ready early, maybe the rider got there late. What can we do in that situation? So still we come back to this, how do we learn? How do we work out what the preparation time was? And the two bits that I think that we can use to solve this puzzle is just those two middle swipes that we had in the previous slide, when the rider arrived at the restaurant and when the rider received the food. Okay, so let's think a little bit how we can use these to work out when the food was ready. So in the situations we were describing before, I said the ways that this can go wrong is either the food waits for the rider or the rider waits for the food. In the case that the food waits for the rider, then when they will collect the food will be when they arrive, plus however long it takes to pick it up. And again, thinking about the flow in a restaurant, when a rider gets to the restaurant, they need to perhaps beckon over some wait staff and ask them for the order, or maybe they have a counter they can go to and to get the attention this way. There's some amount of process there to collect the order. And again, this varies very much by restaurants and how they're set up for Deliveroo, whether they're Deliveroo first or if it's sort of been incorporated into a more traditional restaurant. And so there will always be some amount of time between when they arrive and when they receive, but it will happen fastest if the food is already ready. The alternative is when they arrive early and they end up waiting for the food. In this case, it's probably going to take them the same amount of time to get the food when it's ready, but they can get it from as soon as when it was ready. And so we can reframe this as the time at which they will receive the food should be something like the maximum of when they would arrive or when the food was ready, plus the collection time. But here we have sort of the two aspects of the rider waiting for the food and the food waiting for the rider. Now, for some folks in the audience, you may look at this slide and think, oh, great, we've solved the problem. We have a formulation and there are modeling techniques that you can use on a formula that looks like this. You could enter this into sort of a Bayesian modeling approach and use MCMC to try and solve it. Or for a more classical statistical approach, this looks very much like a sensitive regression. And so you can use sensitive regression to tackle this. That said, those techniques are effective, but they can be a little bit tricky to get to work reliably, and there can be issues getting them to stabilize. They're not the simplest way to approach this. And at Deliveroo, we've always believed from when we started that you should build simple things first and add complexity when it's needed. And so when we first built this, we didn't consider those approaches. And I'm going to talk a little bit about what we did build. We have considered those approaches more recently, although I'm not going to talk about that in today's talk. So what can we do if we don't want to go to a modeling approach that can handle this full equation all in one go? Well, first, it's useful to look at this visually as well. So we have this received, it's the maximum of rider arrival, this ready plus collection. We can reframe this in this way, where we can look at the distribution of collection time versus the rider arrival. So here we have the time the food was actually ready. On the right is the rider arriving late, and on the left is the rider arriving early. In the case that they arrive early, they just have to wait longer until the food is ready, And on the right, they have that fixed amount of wait time. And we can use the shape of this to work out what time the food was ready. So if we take that equation we had before, and instead of having it with a maximum, we can split it apart into its two times. So the time where the rider is waiting, where the food, I have these back to front, where the food received time is when it was ready plus collection. And the time where the food is waiting, where it's based on the rider arrival plus collection. We can reframe the first of these instead of being deciding when the food would be received, but instead work out how long the collection time is. Because the food was already ready and waiting, we know that the collection time will be the time when the rider received the food after they arrived. And likewise, in the case of the second one, we can reframe this to think about when the food was ready. It's based on when the rider received the time and how long it should take to collect it. Now, in the first case, if we can identify times when the food was waiting for the rider, we already just said that we have signals from our rider of when the food was ready and when the rider arrived. In the second case, if the rider was waiting for the food, the thing that we didn't know is when the food was ready, but we do still know when they received the food. And we just worked out how we can work out the collection time. So we can use that first approach of when the food's waiting to work out collection time, and the second approach when the rider's waiting to work out when the food should be ready. And so if we come back to this visual way of thinking of it and look at the collection time versus the food ready time, we can see how this works in practice. The first thing that we're going to have to do is that we just said that we don't know when the food is ready. So if we replace food ready with the target time, the time we would like the food to be ready, assuming that we predict target time correctly, everything still holds the same. If our model is perfect, it'd be identical. And we can hope that it's going to look something similar. In fact, I can pull some data and check. And this is what it actually looks like from our data, where the two axes are the same as we had before. And it shows that pretty much the time that we say when the food should be ready is roughly when the food is ready. Obviously, it's a little bit messier than that simple diagram that I had before, but you can see that it's not completely crazy what I was saying. And so if we remember, we want to take the situations where we know that the food was ready to work out the collection times. Well, from this graph, it does appear that we can probably isolate those times where the food was ready, just based on the rider getting there later than we would like them to have got there. And then from that, we can take the times where the rider got there early. And with these ones, we can start looking at when the food was ready time. So first, we build our own ability to understand what the collection times are. And then using situations when rider arrives early, use those collection times that we got from the rider arriving late to work out when the food was ready. So how would this work in practice? I said I was assuming that the target time was the same as the preparation time. But what if it's not quite right? What happens if we've got that a bit wrong? So let's first think about the situation where we set the target time much too high, and as such, the rider was arriving late. And so we're looking at something a bit more like this. But for simplicity, let's move all the way out so you can't even see the rider needing to wait at all. Let's say that we set the time much too high and the food is always ready, regardless of when we send the rider. In this situation, when we build our model to think about the collection time, well, we should see this constant collection time that we expect. And we'll always say it takes this amount of time to collect. Then when we look at building when the food is ready time, well, we're going to use when the rider collected the food, less the collection time. And given the collection time's constant here, we're just going to end up with when the rider arrived. The rider will arrive early some of the time, and this will cause us to move the target time down over time and should head us towards that correct preparation time that we're looking for. But what about the other way around? What happens if the rider arrives early? So in the situation the rider arrives early, this is when we've set our target time too low and the restaurant doesn't have enough time to prepare the food. In this case, the target time is earlier in this graph. And again, for simplicity, let's move it much earlier into the realm of we're in the continuous decreasing collection time. In this situation, we're going to look at the times the rider arrived late and say we should be able to work out the collection time here. Obviously, this isn't a flat line, as we saw before. But if we use a model which isn't aware of when the rider arrives, it's just trying to work out what the collection time would be here. It's going to take roughly the average of these collection times. And that will be the time we think it would take to collect. Then we can go back and look for the food ready time. And for the food ready time, as we were saying before, it is calculated from when the rider leaves minus the collection time. The collection time here is always going to be less than the food ready time. The collection time for the section where we're working out the food ready time. And so we're always going to move the target time slightly forwards. We're always going to see the rider waited longer than the time we thought they should have waited, which moves our prediction forwards. So this causes us to move the target time higher. And so from these two simple examples, you can start to see how building these two separate models, you end up with the preparation time heading towards the right time, away from that original target that we set. Okay, so this demonstrates how by building these two separate models, we can take an unseen preparation time. We don't know when the preparation time should have been, and start with a prediction of it. And over time, we should see the prediction move towards the actual preparation time. And this allows us to infer what the preparation time was and actually make a prediction of the preparation time. There's a tough question here that you have to ask yourself, though, is in these toy examples, it kind of made sense that we're going to move towards the right preparation time. But will this actually get us towards a stable preparation time? Will we converge towards the preparation time, or will it fluctuate wildly based on those diagrams I drew? I'm not going to go into the maths of a proof here. Some of my colleagues in the past have looked into this and tried to understand whether the model should stabilize or not. And we're pretty sure, and we've had this live for some time, that using this approach of modeling the collection time and modeling the rider arrival time as two separate parts, you do end up to a convergent prediction. It also converges relatively close to the true preparation time and doesn't fluctuate too wildly. And so you can kind of say from there that the problem is solved. We've taken this problem that we don't get to see from restaurants directly when the food is ready. If we ask them directly, it's not clear that we're going to get the right answer. It's not clear that they can consistently give us the right signal, even if they're trying their hardest to tell us the right thing. And use the signals that we do have. We do know when our riders are at different stages in their journeys. This is something that is built into their flow naturally. We can use these signals to calculate the preparation time. But so I've only gone into sort of the setting up of this problem. There's still a load of areas that I've not dived into so far in the talk. I'm not going to go into as much detail into these other sections, but I just want to give a sort of a flavor as to some of the problems that we face when modeling this and the unanswered questions from splitting this out into these two separate models. So the first thing I haven't talked at all about is how do we model those two things? How do we model collection time and preparation time? We have quite a lot of freedom when making our decision about how to model these. We can use anything in our tool set of modeling techniques. Both of them can be constructed as relatively simple supervised learning problems. There is a little bit of nuance here. If you were a little bit too free with how you think about predicting them, then the composite of the two models won't interact correctly. You do have to worry a little bit about, for example, if one of your models is biased in the way the other one is not, you won't necessarily converge correctly. If your collection time model does have a bias, then you would expect that that bias will systematically move your preparation time over time. And so we have to be careful about that. That said, how simple or complex this model is, whether it's linear or nonlinear, whether we use a vast collection of different features about the restaurant, the riders, or orders, none of this breaks the logic of this pattern that we've been describing of how to infer what the preparation time is. I talked about how the model should converge towards the correct preparation time. If we're predicting a little bit too high or a little bit too low, we do expect that the preparation time will move in the right direction. But I've not really talked about how do we start this cycle. We have, as I said before, hundreds of thousands of restaurants in our platform. How do we get each of them to start correctly? And do those first orders matter? Obviously, if we send riders much too early, it's wasting their time. How do we make sure that we don't do something ridiculous when we start? And what if they're very wrong? Will the model converge quickly enough? How long will it take to get there? Understanding whether the model can converge without wasting a lot of our riders' time and having a lot of cold food at the restaurant is very important to make sure we have a consistent experience for our customers. There's also the tough question that I assume that the food would always be prepared as soon as we tell the restaurant that there is this true preparation time that we're trying to observe. Do restaurants always behave that way? Maybe some restaurants don't prepare straight away and are trying to game when we're going to send the rider. Or maybe some of them would wait until the rider arrives. And that can break some of these assumptions. And how do you handle that in the model? These are some of sort of the tougher complications that we're having to ask, how to make sure this works for everyone, regardless of how they behave. There's the question, which is true in a lot of models, of how to balance adaptability versus stability. But in this model, it becomes quite pertinent, especially because if we notice that restaurants are preparing food in a way that leads to negative outcomes for our customers, sometimes we will want to intervene and communicate to them and work with them and educate them to understand the right ways to get a virtuous cycle. There's this problem where if riders end up waiting at the restaurant because the food isn't ready, riders will learn not to like that restaurant, not want to go, and things get worse and worse for our riders and for our customers. And so sometimes we will work with restaurants to improve this. Also, not every restaurant is mature in their experience doing delivery orders. Over the past years, we've spent a fair amount of time with some of the big partners working on the correct way to do food delivery, as we were still working out how to have a restaurant that both does dine-in and delivery. How does our model adapt to this and make sure that we forget the times where they hadn't changed the behavior, when they had changed their behavior? But still work for the smaller restaurants where they're behaving consistently, but they don't have the same volume to have the stability of their predictions. Again, it's a difficult balance, and how we get this to work for a large number of restaurants is not obvious at all. And then we can go into how much do we generalize versus specialize the model. Naively, you kind of want to generalize across restaurants. It feels like preparing food should be something which we can learn from one restaurant how another one prepares the food. And you start to ask yourself things like, well, what about the restaurants can I use to generalize? Maybe their cuisine would be really helpful. But then you have problems that maybe you have a burger restaurant, and do we expect McDonald's and Five Guys and GBK to all prepare their burgers in the same amount of time? Is the way GBK behaves useful to understand how McDonald's should behave? And we also have problems like, if you consider Chinese, for example, you can have your local Chinese. And then on Deliveroo, we have Hakkasan, who are Michelin-starred restaurant. Their orders are significantly more expensive than others. How do we handle the fact that some restaurants have such expensive items on their menus, where others have really cheap ones? We expect that the more you order will cause the times to increase. But how can we start that out if we've not seen orders from you yet? When the Michelin-starred one enters, or when the McDonald's enters, how should we know that this one's expensive versus this one's cheap? And again, how do you get this to scale to 130,000 restaurants? It's a little bit complicated, and certainly predictions can go very wrong if you try and generalize too much here. And then finally, I just want to say how specific can we be? Even within a restaurant, so I was talking about between restaurants, comparing our Hakkasan and our local Chinese, and the value of the orders can vary wildly. But even within a restaurant, you can have different items on a menu that are very different in terms of their preparation time. Maybe you can have a can of Coke on the same menu as a barbecue restaurant that wants to smoke their meat and will take 10, 15 minutes to produce that. How can we tell the difference between it being 5 of those versus 5 Cokes? It seems pretty easy looking at a single order, but once you again scale this out to 130,000 restaurants, and you have the restaurants able to modify their menus over time and onboard themselves, this becomes a much more challenging problem of how do you identify these 2 different types and use that in the preparation times. These are a lot of the challenges that we face adapting this approach to all of our restaurant partners. We have some ideas for some of them, and we certainly don't have ideas for all of them. These are the fun challenges that we're still thinking hard about in terms of how to get our preparation times to work as effectively as possible. But that's a summary of the way our preparation time model works. I hope it was interesting to hear how we handle predicting a preparation time that we don't really get to observe, and some of the challenges that we face still trying to model. Do you have any questions?
Ben, thank you very much, man. What an interesting challenge to be working on, and it's definitely given me, man, that was nearly such a bad pun. I nearly said food for thought. And now I'm secretly quite pleased with myself. So yeah, it's given me a lot to think about. So really interesting. I have been in a bit of a habit of, if you're out there in the online world, drop us a little message in the chat. As I mentioned at the start there, Ben's obviously given up his time to come and share with us. I would love a virtual round of applause, just to let Ben know that there are people out there watching along at home, and I'll give a few of you a shout out as they start to come in. So first of all, Joe Hartshawn, that was great, Ben, with a round of applause. So we've got an anonymous one coming there. Excellent talk, thank you. Mateus, round of applause. Man, they've shot past me straight away there. So Joshua Samuels, thank you, Ben, super insightful. Sai, thank you, Ben, for the informative session. Candace, clapping emoji. Nay said, hi. So we've got a question there. If you have questions, please stick them into the Q&A and we'll get into them now. But Steve Cook, Christian, Anthony, Matt Jones, Martina Jones, Fedel, Phoebe Rowe, round of applause, Julia, Maria, Francis, Jonathan Taylor, the list goes on and on, Ben. So you have been very well received by the online Data Science Festival community. So thank you very much for that. There are some questions coming in, which is great to see. Ben, if you'd like to, at the same time as I'm just going through these questions, you can read along in the background. I'll run through them in order. So actually, I may jump around a little bit in the order, but we'll start with Phoebe's question there at the top. So Phoebe, great to see you online. I know you've been a great supporter of the festival, and you're hoping to get down for the in-person event. So look forward to seeing you there as well. Phoebe's question is, thanks for the talk, Ben. Really interesting. Which bad scenario is more important to avoid? Food waiting versus rider delivery? Do you adjust the model to account for this?
It's a very difficult question to give a definitive answer to in many ways. The cost to Deliveroo and the cost to the players of our marketplace are different for each of these situations. Riders really don't like waiting at restaurants. It's a very frustrating experience to be waiting at a restaurant. It feels like you're not doing anything, and it feels like you're not earning. And it's hard for us to pay appropriately for this without making a situation that the riders can game really easily. So waiting for the riders is very frustrating. But on the flip side, if the food's waiting, then the food customers get cold food. They are very different in terms of the ways in which the costs come in. And I don't have a really good way to say definitively which one is worse. But definitely it's something we need to be very careful of in how we balance. You can tell if you look at that modeling that we are aiming for that minimum collection time So it sort of implies that we're trying to hit the sweet spot, and that the rider wait time is really important for us there.
Perfect. Thank you very much. Noor's been in the Q&A just to tell us it was a fantastic presentation. So thank you very much for that, Noor. Great to see you as always. I'll jump onto the question there from Jonathan Taylor. Thanks, Ben. Very interesting and surprisingly complicated, even with some basic maths. You just went into this a bit, but how do you factor in the minimum times for preparing a dish or a rider getting to the restaurant? I.e., you can't just pick some preparation time out arbitrarily. There are limits.
So the main way that we're concerned about with a minimum preparation time is not necessarily that there should be a true minimum preparation time. There are partners on our platform that can prepare things incredibly quickly. We have a lot of convenience stores and we have sort of alcohol stores. And if you order 2 bottles of wine, how long does it really take to prepare that? Likewise, we've released our hop experience, which is the sort of our 10-minute grocery offering. And we've put a lot of effort into there to make sure that preparation times are incredibly small and that the food will be ready very quickly. Mm-hmm. And so our main concern with the small preparation times is, will it work well with our systems? Will we end up telling the restaurant at the wrong time when the rider gets there? And so the harder part to align with the very low preparation times is making sure that the rider gets there at the right time and it doesn't end up sitting waiting for ages. And so that's our primary concern. And as you allude to, you get into the minimum travel time is. The minimum travel time is purely based on what we can predict. If a rider stood outside a restaurant, how long will it take them to get inside? It's actually kind of a curious question. It's not always obvious how long it will take them to get there. And that's sort of the gate on how we think about the minimum that the prep times can take.
Perfect. Thanks very much, man. Question there from Joe Hartshorn. How do you address bias, particularly different bias between the 2 models?
So the significant part in terms of getting the models to converge together is making sure that their biases interplay nicely. So you got to make sure that you're treating your data in the same way for both models. If neither of them are biased, then the maths works out. In fact, the maths I talked about that has been done to prove convergence assumes no bias. And so typically we would just use an unbiased model here. This can lead to issues in that preparation times obviously are zero capped, so have a long tail distribution. And to do this correctly, to do it very well, you would have to take that into account. But if you use unbiased models, then you should end up with the right conversions.
Perfect. Thank you very much, Ben. Question from Justin. Fascinating talk. Thank you. You kind of touched on it as a problem, but do you have a current cold start solution for adding new restaurants that you don't have any data on? Yeah, I imagine that's an even more complicated problem there. So yeah, how do you approach these new restaurants being added to the platform?
Well, in some ways it's very complicated, but our solution is very simple. We ask the restaurant how long it will take them to prepare food. And to begin with, we just use the time that they tell us. So we rely on our restaurant partners giving us a good place to start. Obviously, if they set this very wrongly, and we do see situations where it's set quite far away from where it should be, it does make our systems not behave well. But normally this makes the experience for the restaurant worse. So we do actually have aligned incentives, I think, at least to begin with, for getting these preparation times set correctly.
Perfect. Yeah, thank you very much. I guess as well, it probably also depends, who's working in the restaurant on a particular day. Yeah, who's the most efficient staff members? So, cool. Question from Christian. Thanks, Ben. Super interesting problem. Do you reward consistent and/or quick restaurants?
We don't do anything directly to reward them. One of the things we have talked about occasionally is whether we should do anything on the other side, whether we should penalize restaurants that don't prepare food consistently. But we don't have anything on the reward side directly. The thing that does happen, if restaurants are consistent, and it means that the prep times we predict are the right sort of numbers, they're going to give a better experience to their customers, because we can say better when the food will arrive. Riders will like going to the restaurant more, and so they'll have a more consistent experience with their riders. And it is in their best interest, and naturally, the different sides of the marketplace will work better together if they do this well. But there's no direct incentives that we give.
Yeah, you're juggling three sides there, which I imagine brings up lots to think about. Question from Vipul. Thanks, Ben. Very interesting and thought-provoking. One question: how much do you think this is an operational solution or problem? How many riders do you have, etc., versus a data science solution?
So obviously, the two sides can't operate without each other. The data science solution is useless unless our operations are sound. But equally, operationally understanding what the best solution to reach and to have the system working properly, the data science side becomes important as well. It's sort of the intersection between the operations and data science that will make this overall successful.
Perfect. Thank you very much. Question from Tiffy. I don't think this one has been covered yet, but if it has been, obviously just let me know. But Tiffy, thanks for the presentation. May I ask, how do you combine the two separate models so it balances the correct prediction and accuracy?
I'm not sure how directly to answer this. The system's designed such that we should be able to get to the right prediction. Obviously, the accuracy of both models is important to improve the overall accuracy of the food preparation. But I don't know if there's anything I can think of particularly that we do beyond the normal modeling strategies you'd use to make this work better.
Perfect. Thank you very much. I'm going to shoot down to the question from Juan there. He's done two in one. I'll maybe ask them separately if we've got time and see where we go. But first question there, during the project, did you quantify the business impact in pounds of making wrong estimations to other stakeholders?
Yes, for sure we did. Definitely, I was talking about the different costs to getting this wrong. If we predict too high and too low, having the food and the rider waiting. Obviously, it's very important when we make changes to this that we understand what the costs are involved. I don't have any specific numbers that I can share today, but yeah, we definitely thought about this carefully when making changes to this.
Perfect. And when you look at changes, leads kind of into question two there. Do you run any A/B tests, and do you have any concern about the interaction of drivers, restaurants, e.g. two-sided market network effect?
Yes, so at Deliveroo, typically most changes we make, we're running experiments to validate them. And as we've changed this model over time, we've run experiments to see what the consequences of the changes are. I think there's a couple of interesting things to call out as challenges to experimenting on this model. One is I described how if we're over and under predicting how the model should be able to get to the correct preparation time. But that still takes some amount of time to get there. We have to allow, if we change the model, for it to converge on the new preparation time. And so we have to be a bit careful to have the conditions both be able to converge and to compare at the appropriate time to make sure that we're comparing it right. And then, as you say, there are also broader interaction effects. One of the non-obvious ways this can interact is through two restaurants near to each other. If we give them different models that change their preparation times, one higher and one lower, well, that's going to interact in terms of how the customer sees these restaurants. And so you have to be kind of careful when designing the experiment here. And it is a little bit tricky to get useful inference and get sufficient power because of the limitations of how we experiment on this.
Thank you, Ben. That's absolutely spot on. Thank you. I'll jump to the question there for Matthew and obviously come back to some of the others as well. But Matthew's interested to know, how much information do you share back to the restaurants when they receive more orders, average prep time, would the data you collect be useful to them? And I guess perhaps sometimes they'll be looking at the platform and you're saying, oh, the food prep time's 30 minutes or whatever. And they're like, no, it's not, it's 15 or whatever. And obviously you've got the data to back it up. So yeah, how do you go about interacting and feeding this stuff back to the restaurants?
Yeah, so this is something which we've been evolving over time. And I think we still have some ways to go to be as good at this as we would like to be. We do have an interface that restaurants can access their data and they can see the predictions we've been making for their prep times. But definitely there's more that we can do in terms of sharing data here and being a great partner to our restaurants and through surfacing this information.
Perfect. Thank you very much. The question from Alex McNulty. Thanks, Ben. Love the overview and sharing such a complex problem so well. I know that riders get multiplier incentives for certain times during the week. How does this impact your models?
So the construction of this model is the thing that it cares the most about is when the rider arrives at the restaurant relative to when the food should be ready. The rider incentives are primarily driven by whether there's an imbalance in how many orders we're receiving and how many riders we have to deliver them. In the case that we don't have enough riders, that's when the incentives would start to be used. We control when we tell the restaurants about orders, as I mentioned at the beginning. And this means we can respond to those sorts of imbalances by not telling the restaurant about the order until the right time for the rider to arrive. And that means we can still use this modeling strategy regardless of the state of the network. So it's resilient to the supply issues, which those incentives are designed to help with.
Perfect. Thanks very much, man. There's a couple of questions there left in the Q&A, Ben. So if you just want to have a quick look at them and let me know whether we've got time or you're happy in terms of discussing those. And I'll just quickly jump back into the chat because there's been some 25 messages coming on the chat. So while you're having a quick look at that, I'll fire through some of these. So yeah, Anwar, great talk. Matthew Hale, thank you, great talk. Thordis, thank you. That was great, really interesting. Olivia, Anthony Paul, Nordin, Aidan, Juan, Answar again, brilliant. Alex, yeah, Alex, question there. So yeah, absolutely loads of people in the chat, which is absolutely awesome to see. And thank you all very much for doing that. In terms of those couple of final questions, Ben, does that kind of make sense? Are you happy to pick them up?
Yeah, I only really have an answer for the top of the two.
Okay, perfect. So we'll start with that one then. Question from Daniel. Not having data for your target variable, how do you avoid doing supervised learning?
So while we don't have a target when we start this exercise, we managed to split our data into those two separate sets in order to have a model with a target for the first set to work out the collection time. And so then we can use our supervised approach to predict collection times. Then we take that model that we derive for collection times and apply it to the situation where the rider arrived early. And this allows us to infer our target variable. So we didn't have it directly from our data, but utilizing that model that we construct a target variable that we infer, and then we can again use our supervised learning techniques. And so the trick of what we're doing here is reforming the data into a way we can use those supervised techniques.
Perfect, mate, that's awesome. Thank you very much, Ben. We did ping Ben's LinkedIn profile into the chat at the very beginning. So Ben's kind of said to us, you know, he's happy to hear from you. So if there is any follow-up questions, interest in Deliveroo as a whole, hiring even, you know, please do follow up with Ben. Or if we didn't get to your question or you think of a question after, please do that. We did talk very briefly about A/B testing. It's worth just calling out that Matthias from Deliveroo is joining us at our in-person event on the 27th. Specifically, he's going to be talking about measuring churn in online experiments. And I know he has been a previous speaker for us before, and he is definitely a man worth coming to see in person if you can. So just to draw things to a close, Yeah, I just want to wrap it up, Ben, by once again saying thank you. It's definitely a real indication of how successful the talk was, given by the chat. Number of questions we had, definitely nice and interactive. And yeah, you've absolutely flew through all of the questions that came in as well. So mate, thank you very much. And yeah, how did you find it? How was it speaking at the Data Science Festival online?
Yeah, it was a lot of fun. Thank you for having me. I got a little bit concerned part of the way through that I was going too fast, but it looks like, at least with the questions as well, we've done pretty well for time.
You're a professional, Ben. You're a professional, man. We'll be getting Shane to wheel you out at future events as well. So I'll let Shane know what a great job you've done, man. So yeah, thank you very much. And thank you all for joining us at home as well. Definitely like to just kind of wrap up by saying thank you to Deliveroo as an organisation. Everyone that we deal with at Deliveroo is absolutely fantastic. Ben mentioned it at the start. He works with a load of really smart people. That goes across the whole organisation outside of tech as well. And as I say, very forward thinking to support our community and do all the good stuff. They don't necessarily have to sponsor the festival, but they do it anyway because they love to see the data community grow. So thank you very much to Deliveroo. So I will draw things to a close now. Thank you very much, Ben. Thank you for joining us at home, and hope to see you at future events online or in person soon.
Thank you very much.
Perfect. Thanks very much, everyone. Bye-bye.